Good morning, all of you. Myself, Dr. Manmohan Singh Yadav, Assistant Professor in CSE AI Department in IIMT College of Engineering at Noida. Now, today I present the topic in data structure. In data structure. This is the subject in computer science, which is data structure. In data structure, we discuss a particular topic is known as the V tree. Now, these are the presentation outlines. First of all, introduction to B tree, and second, operation on the B tree. And there are the many operations like searching, inserting, deleting, creating, and traversing. These are the basic operations which perform in the B tree. Now, next point is the searching in B tree, inserting in B tree, deleting in B tree, and last is the application of the B tree. These are the presentation outlines. Now we move on the first introduction part. We start the B tree. First of all, we know the tree. Tree is the data structure, which is a non-linear data structure. B tree is a non-linear data structure which store the data or information in a particular node form. And there is the different node to store the data in a particular node, and there is the different childs like left subtree and right subtree. These are the childs to store the data in different access. These are the introduction part of the tree. Now we move on the particular tree known as the B tree. Before the B tree, we also known as the BST, binary search tree, height balance tree, and these are also a tree, B plus tree and B tree. So we take a particular topic known as the B tree. What is the B tree? B tree is a specialized form of the MW tree, which can widely used in for disk access. We It is stored the large amount of data in a hard disk. So we store the data in hard disks. We use the technique known as the B tree. A B tree of order M can have at most M minus 1 key and M children. And, and the main reason of the using the B tree is the capability to store the large number of key in a single node or a large key by keeping the height of the tree relatively small. In the previous topic known as the height balance tree or BST, it is not reduce the height of the tree. In the B tree, we reduce the height of the tree. What is the benefit of the reducing the height of the tree? We use height of the tree. It is minimize the searching time and accessing time. Timing is depend on the height. So we reduce the height, it maintain the logarithmic algorithms. So now we can using the B tree, it is capability to store the large number of key in a single node and large key value by keeping the height of the tree relatively small. A B tree of order M contains the property of the M-way tree. In addition, it contains the following property. Beside the B tree, MV tree, we use the special property of the B tree. First property, every node in a B tree contains at most M children. If a particular node have contained the order M, then they are the M minus 1 key values and M children values. So next point is that every node in the B tree except the root node and leaf node contains at least m by 2 children. And next point, the root node must have at least two nodes. All the no, leaf node must be at the same level. It is not necessary that all node contains the same number of children, but each must have m by 2 number of key. Now we take an example, particular example. If you have a order M, then uh, here we take an example, a B tree of order 4 shown in the figure. Now we take 60 is the root node, and 29 and 32 is the next node which contains the two values 29 and 30. This is the left subtree, and now we move on the right subtree. In the right subtree there are the two key values 90 and 98. So these are the structure of the B tree. We insert one by one node in the B tree, so we can see height of the tree is reduced. While performing the some operations on B tree, any property of the B tree may violate such a number of minimum children a node can have. To maintain the property of B tree, the tree may split or join. Now we move on the operation on the B tree. We already discussed there are the different type of the operations like creation of the B tree, searching of the B tree, inserting of the particular key values in a B tree, and if we want to delete a particular node, so we perform the deletion operations. Now first of all, discuss the operations searching in the B tree. In a searching means we search a particular key values in a B tree which is already stored in the database. So we perform the different type of the searching operations. Searching in the B tree is similar to that in binary search tree. For example, if we search an item 49 in the following B tree, we take example in next slide. So the process of something like this: if a particular value is searched, then we compare the first node to the root node. If a root node is matched, then search is successful. If a root node is not matched and its value is less than the root node, which is the searched, so we searching is start in the left subtree. If searching value is greater than the root value, so we start the searching in the right side. We take a particular example. If we want to search a 49 values in a, now you can see this example. 79 is the root node, and 1456 is the left subtree, and 89 and 101 is the right subtree. So we want to search a particular value 49. Now we can see where is the 49. 49 is this. Now we can see the 49, but the process of searching is, first we start the searching to compare the 49 with the 78. So 49 is the less than the root node 78, so we search the left hand side. That means the left subtree. So we compare the 40 and 56. So 49 is the in between the 40 and 56. So we move on the 40 towards the right subtree. We can see the 49 is the right side of the uh, key values 40. So we can see here is the 49. So we can search a particular values 49, then search is successful. So stop the process. These are the process of the searching. Now another example we can see search in the B tree. We also take another example like search key 71. Now we can see the 71 is where 71 is the right side of the root node. So first of all we compare the 71 with the 25 and 62. uh, 71 is the greater than the 62, so we search in the right hand side. So we start the right hand side, we take 73 and 84. So 71 is the less than the 73, so we move on the left hand side of the key value of 73. So now we can find the 71 is here. Now we move on the next operations, insertion operation. in B tree, we insert a particular value in a B tree. First of all, if tree is already created, so we insert a particular node in a particular place. So we take the following steps to insert the B tree. Insertion are done at the leaf node level. The following algorithm need to be followed in order to insert an item into the B tree. First of all, we traverse in B tree to find the appropriate leaf node at which the node can be inserted. Uh, Next steps, if the leaf node contains less than m minus 1 key, then insert the elements in, in increasing order. We also know the we inserting the values in the B tree or creating in the B tree, we insert each element in sorting sequence. So we can take a particular steps to, if the leaf node contains the less than m minus 1 key, then insert the elements in the increasing order. Now we move on the third step. Else, if the leaf node contains m minus 1 key, then following steps is followed. Insert the new elements in the increasing order of elements. Split the node into the two node at medians. Push the median elements up to its parent node. Next step, if the parent node also contains the m minus 1 node of the key, then split it to the following same steps. Now we take a particular example to inserting the values. Here we take an example, node is root node is the 60 and other left subtree and right subtree is here. So 8 will be inserted to the right of the 5. First of all, we want to insert the value of 8. So here we find we move on the particular node. So we compare the 8 with 60. So 8 is the less than the root node 60. So we move on the left hand side. Uh, in the left hand side, 29 and 32. So we compare the 29. 8 is the less than the 29. So we move on the left subtree of the 29. So here values is 3, 5, 10 and 23. So we insert the value 8 in particular positions 8 in a particular node. The node now contains the 5 key, which is the greater than 5 minus 1 equal to 4 key. Therefore, split the node from the medians 8 and push it up its parent node. So in the following, we know particular rule in the B tree, if a key value is m minus 1 and children is m. So here we can see if order is 5, then we know the 3 value, 5 value, 8 value, 10 value and 23 value. These are the maximum value of the key value, which is not less than 5. So values 3, 5, 8, 10 and 23, it is a maximum value of 5. So we split the node. In which place? We particular median values. We find the median values here. Median values is what? Median value is 8. So we split the 8, means we move the 8 in upward. Now you can see in here example, 8 is moved to the next parents node. So we can see the 8 of the left subchild is 3 and 5 and 8 is right subchild is 10 and 23. So these are the process to inserting a particular node in the B tree. Now we inserting values. This B tree is also work on the alphabets number and numeric values. So both elements are inserted in a B tree, numbers and alphabets. So we take a particular example, uh, alphabets. So now we can see the values here. insert GMPX. These are the root node and which contains the value is four values, and order is three. Here T is three, and we also know known as the maximum tree is the 2T. 2T which is contain the children, and key value is 2T minus 1. So we take an example, insert B. When we inserting the B, now we can see here is the B. After inserting the B, the maximum node is 1, A, B, C, D, and E, which is the maximum value, maximum order key values. So we split the values key. Now we move on the next slide. We insert the A, B, C, D, and E. Now we take the another example, insert Q. In the above figure, above example, we insert the value Q. When inserting the value Q, we take Q is which position? First of all, we take the Q is which position? Q is position on the uh, right side of the P. So now we can see here is Q is inserted. Okay, now you can see the Q is inserted, but in before inserting the Q, we move the T values in upward side. Why? Because the maximum elements are is key value is maximum. R, S, T, U, and V is the maximum, and we want to insert the Q. Q is also a maximum values. Means order of value more than the order values. So we split the node here R, S, T, and U, V in a median values. Here the median value is T. So we move on the T in upward side, and R is in the right side. Now next inserting elements is we insert the L. We insert L in particular example. Now we can see where is position of the L. L is the position of the J, K, and L. Now you can see less than value of L is the M. So now we insert the value L. Now also inserting process is insert F in the above diagram. So insert F. First of all, we take the where is the position of inserting the F. F is inserting to the right side to the left side of the G. A, B, C, D, and E. So we insert the F. First of all, we split the A, B, C, and D, and position of the C is we move the promote to the C in parents node, and other AB is split in another part, and DEF is split in another part. So we insert F at like this. Now we take a simple exercise for the students to exercise inserting a B tree. Uh, Inserting the following key in B tree when T is equal to 3. So this is for the practice for the students to inserting a particular these elements like 3, 7, 9, 23, 45. These are the process to inserting the elements. Now we take another example inserting B in operations. There is the three cases in when inserting the operations. The leaf node has room for the new key. If we want to insert the three, first of all we take the position of the three. Now we can see in example three is in the left hand side of the uh, left subtree of the tree. So 5 and 8 insert 3 in order where we insert the 3 at particular position. This is the another example for in previous example also for practice, but here we also give the another example so for practice. These are in the previous slide we can see these are the case 1, and next these are the case 2. In case 2, we insert the values 16. So we can also see Where is the position of the 16? Now we move the 16, particular search the position of the 16. So we can see the 16 in between the 10 and 19. So we insert the right side of the 19, right subtree of the 19. So we can find here 14, 19, 20 and 23. So we insert the 16 in particular positions here. Now in case 2, the leaf in which the key is to be placed is full, then leaf 2 increases the height of the tree. If leaf node is the full, then increase the height. So this is the process of increasing the height in another tree. These are the also example for inserting the elements we already discussed in the previous slide. So move on the next operations. Now we move on the deletions operation in a tree. If we want to delete a particular key elements in the B tree, so what is the process for deletion of the key? Because we maintain the property of the B tree. There are the property of the B tree we discussed in the previous slide. What is the property of the B tree? Because it maintains the minimum number of key m by 2. These are the first property. Each element, each node have the minimum value is m by 2, and maximum value is the m. So these are the properties of the deletion of the B tree. Now here we take it. Deletion is also performed at the leaf node. The node which is to be deleted can either be the leaf node or an internal node. First of all, we take the node. It is a leaf node or a internal node. The following algorithm needs to be followed in order to delete a node from the B tree. First step, locate the leaf node. If we want to delete a particular node, first of all we apply the traversing operations and find the particular elements in a B tree. So this is the steps to locate the leaf node where we want to delete the particular elements. Now second step, if there are the more than m by 2 key in the leaf node, then delete the desired key from the node. So if the leaf node does not contain m by 2 key, then complete the key by taking elements from the left siblings and right siblings. If the left sibling contains the more than m by 2 elements, then push its largest element up to its parents and move the intervening elements down to the node where the key is deleted. This is the first steps if elements are not more than the m by 2 key elements. Now, second step, if the right sibling contains the more than m by 2 elements, then push its smallest element up to the parent and move intervening elements down to the node where the key is deleted. If neither sibling contains more than m by 2 elements, then create a leaf node by joining the two leaf node and intervening elements of the parent node. If parent is left less than the m by 2 node, then supply the above process in parents nodes too. Now we take a particular example for deleting a B tree. If the node which is to be deleted in an internal node, then replace the node with its in-order successor or predecessor. Since the successor and predecessors will always be on the leaf node, hence the process will similar as the node is being deleted from the leaf node. Now we take a particular example to delete a node. So here the figure which is the root node is 90 and the left subtree and right subtree is also mentioned here. Example 1, delete the node 53 from the B tree of order 5 shown in the following figure. We know we want to delete the node 53. First of all, we apply the traversing process to reach the particular node 53. Now in figure we can see where is the node 53? 53 is the left 53 is the less than the 90, so it is the left in the left subtree 49, and compare the 49 and 60. So 53 is in between the 49 and 60. So it is, we can see 60 left subtree is the 53, 53 and 57. So we can see the 53 is here. So we want to delete the 53, but we deleting the 53 only one node in the uh, in this node, only one key elements in this node. So we can't delete the 53 because it is the property of the B tree which have the minimum number of keys m by 2, where m is the order. So 53 present in the right child of the elements 49 and delete it. So we can see 57 is alone and which is not follow the deletion property. Then what? Now 57 is only elements which is left in the node. Minimum number of elements that must be presented in the B tree of order 5 is 2. It is less than that of the elements in its left and right subtree are also not sufficient therefore. Merge it with the left sibling and intervening the elements of the parents, i.e. 49. The final B tree are shown in the following figures. Now we can take the here 49 53 means 23, 34 and 57 and 49. These are the merge in a particular elements. Now we can see the here we merge the 23, 34, 49 and 57 in a particular node because we maintaining the particular B tree property. Now we take deletion from the B tree and another theory and concepts. So they are the definitions in a previous slide. We can also take the examples where we take a order of the tree is 2 tree, where T is the order. Now we can see also the insertion of the B tree where we can also use in the B tree. So we move on the next slide. Now look at an example. We are giving this valid B tree. We take order is t equal to 3. So we delete a particular elements. We can also deletion process in the alphabets number which is stored in the node are numbers. In a previous slide, in a previous example, we can see the numbers are deleted from a particular B tree. And now in this slide, we can deletion process from the alphabet. Okay. Now deletion have the different cases we discussed in previous as case 1, 2, and 3 because particular node in a leaf node and which have the sibling is the minimum node m by 2, and this is the process again we repeat the process uh, in the deletion case. Now we take the case 1. If the key k is the node x and x is the leaf node having at least tk, then delete k from the x. If here we can see node is x and k is the node which is one to delete, and property is uh, tk means which is greater than the key elements. Now in this process we easily delete the k value from the particular node, which is also maintain the property t minus 1 elements. Now these are the cases from different slides. We take an example in case 1. We delete f. We can see where is the f is here. How can find it? We compare the f value with p, means root values. we compare the root value p to the f value, and we delete to f. Here the minimum node is D, E, and F, so we can easily delete F from the key. There is it maintains the minimum value is 2, so we can easily delete F from the node. Now, in the sub case of A, if the child Y that proceed K has at least T key, then the predecessors of the K dash of the key in subtree rooted at Y. Recursively delete K dash and replace the K by the K dash in X. Now we can see here example in figure for particular node X, and we want to delete the K value, not a leaf node, it is not a leaf node, so it maintains the property of key m by 2. So now we can delete the k dash from the figure easily. Now we move on the deletion case. Next point, sub case is C, where we want to delete the k in particular node X, and left sub left sibling and right sibling is also maintain the t minus t minus 1 key elements and t minus 1 key elements y and z. So then what? Then in this case we merge the all the elements in particular node. We can see merge y, z, and k. So combine in the particular node. Combining and deleting, we also discuss here combining these elements, and these are the examples to combining and deleting the elements. Now we move on the next point, next case, sub case 2. Ci of x has t minus 1 key. Some sibling has at least t key. Now we can see in figure we want to delete k elements, and k1 and k2 is the root node of the left subtree. So we can easily recursively delete it from the k in this way. These are the deletion process of B in the previous example. We can see the where is the B. B is in this left hand side of the C root node. So if we want to delete the B, then A is alone. It is not follow the minimum property of the B tree, which have the m by 2 elements. So we can after deleting the B, we merge the A and root node of the C and E, J, and K. So we merge this process to maintain the property. Now in sub case of the B also can merge recursively in the above examples. Both sibling have the t minus 1 key. It means K1 has left subtree t minus 1 key, and K1 has right subtree t minus 1 key. Then what? In this case, we merge all the elements, means Cix and Ci plus 1x, and also the parent node in a particular node. So these are the example on the base of the case 3. So now we delete the elements D. So where is the D? D is in this position. So we can delete this elements from the leaf node. There are the simple examples here to deletion process, assuming the 5-way tree A and B tree also. We want to delete the 2, we can easily delete in this process. These are the simple example to exercise. So where we want to delete, yes, we can delete the elements in the particular elements. If we want to delete the 43, then we move the 56 in the particular positions. Now if we want to delete the 50 in a few key, now we can see if we want to delete the 72, then merge all the root node. We can see in figure join back together 56 31, 43, and 69 in a particular node. Now we can see here 31, 43, 56, and 69 in merge positions. Merge all the sibling values. Now these are examples. Now next is the application of the B tree. Here we discuss the application of the B tree. In the B tree is used to index the data and provide the fast access to the actual data stored in the disk sense. To access the value stored in the large database, it is stored on a disk, a very less time consuming. Searching in an unindexed and unsorted database contains the n key values. We need the order of n running time in the worst case. But in the B tree, if we use the B tree, then index in this database, we can search the log of n times in the worst case. These are the applications in the B tree. Now another example applications and issue in the B tree. In B tree, accessing data in sequential order is not efficient. In order to traversal of the B tree required many disk access. Now we can see they are the different type of the data points to search a particular elements or store the data points in the B tree. Now okay, thank you.